Let's look at a modified version of OpenStax University Physics Volume 2, Chapter 7, Problem 60. A metallic sphere of radius 2 centimeters is charged with plus 5 microcoulomb charge, which spreads on the surface of the sphere uniformly. The metallic sphere stands on an insulated stand and is surrounded by a larger metallic spherical shell of inner radius 5 centimeters and outer radius 6 centimeters. Now, a charge of negative 5 microcoulombs is placed on the inside of the spherical shell, which spreads out uniformly on the inside surface of the shell. And here is where I modified the problem. I'm asking a different question than the problem did originally. What is the electric field at r equals 1 centimeters, r equals 3 centimeters, r equals 5.5 centimeters, and r equals 7 centimeters if all these distances are measured from the center of the sphere? So, I won't write down knowns and unknowns because I have all of the information that I need on the diagram itself. And so let's just repeat what the problem says. We know that there is a sphere that has 5 microcoulombs of charge on it. And then there is this spherical shell that has negative 5 microcoulombs on it, and the problem told us that the negative 5 microcoulomb charge were distributed on the inside of the spherical shell. And that makes sense because the positive 5 microcoulomb charges will attract negative 5 microcoulomb charges as close as they can to one another. And that means that all of these negative 5 microcoulomb charges will be on the inside of the shell and none will be on the outside of the shell. All right, so we're looking for electric fields at various distances. Now, this beautifully spherically symmetrical diagram should clue us in that the type of problem this is a Gauss's law problem. So, in part A, we want to find the electric field at a radius of 1 centimeter. So a radius of 1 centimeter would be somewhere inside this sphere. So let's draw a Gaussian surface there. Something like that. And when we write down Gauss's law, some of the electric fields that are perpendicular to the area or parallel to the area vector is equal to the charge enclosed by the Gaussian surface divided by epsilon naught. So if I look at the charge enclosed by my Gaussian surface, there's nothing here. All of these plus 5 microcoulombs are distributed on the sphere itself, so there are no charges inside here. So that means that Q enclosed over epsilon naught is 0, and that also means that the electric field at that location is 0. Now let's look at part B. And again, we start with sum of the electric field cosine theta delta A is charge enclosed divided by epsilon naught. And we will now draw a Gaussian surface at a radius of 3 centimeters. So that is outside the sphere, somewhere here. And now when we're looking at the charge enclosed, the charge enclosed in my Gaussian surface is the plus 5 microcoulombs. So I'll write that as plus 5 microcoulombs divided by epsilon naught. But now, what is the left side of the equation? So we know that the electric fields from the positive charge are going to go radially outward, and the area vector is also radially outward. It's perpendicular to the tangent at that point to the sphere. So that means that cosine theta will just be 1, and the left side of the equation is just E times the area, the total area of the sphere. So that's 4 pi r squared, and that's equal to my plus 5 microcoulombs divided by epsilon naught. So when we solve for the electric field, that becomes plus 5 microcoulombs divided by 4 pi epsilon naught r squared. 4 pi epsilon naught is k, so that's 9 times 10 to the 9th times 5 microcoulombs divided by the distance. So for part B, that is 3 centimeters, so that's 0.03 meters quantity squared. So the electric field then will be 5 times 10 to the 7th volts per meter, or newtons per coulomb. Either one of those units works. All right. For part C, so now we want the electric field at 5.5. So I want to draw a circle. Let's see if I can manage that. Inside here, the circle in the problem is not circular. So the electric field is inside my spherical shell. And now if I write down Gauss's law, so I have sum of electric field cosine theta delta A is charge enclosed by my Gaussian surface divided by epsilon naught. The charge that's enclosed is the negative 5 microcoulomb charge that distributed itself on the inside of the conductor plus the plus 5 microcoulomb charge. So this will be negative 5 microcoulombs plus 5 microcoulombs divided by epsilon naught, and that is 0. So that means that the electric field at that location is also 0. And we also already knew that. We know that this shell out here is a conductor, and we were looking for the electric field inside a conductor. We know that the electric field inside of a conductor is 0, so that should not come as a surprise. In the last part, now we want the electric field at a distance of 7 centimeters, so that is outside the shells, so somewhere out here. I should make that bigger if I can. I don't know how. All right, so we want the electric field outside the sphere. So when we write sum of the electric field cosine theta delta A is Q enclosed divided by epsilon naught. The charge enclosed by the Gaussian surface is all of the charge in the problem, so that is plus 5 microcoulombs minus 5 microcoulombs divided by epsilon naught, so that's 0, which means that the electric field outside of this configuration is 0.